this episode, we talked to Daniel Ritchie, who works on neurally guided procedural models. The work that I ran into was on creativeai.net, and you put this input as, say, a target, maybe the letter D, and the output is these vines with flowers in the shape of roughly of a D. And so you can basically give these different inputs, and then it has a particular output in a different structural texture, for lack of a better term. Daniel takes us through a live demo on the web that you'll be able to play with, and I'll put the link in the description. And he also does it with lightning and these vines. And so you can have this ability to say, hey, I want it in this shape, and then you output it and to see that. The original inspirational research that Daniel was motivated by had these procedural generations that took an hour, maybe 2 hours, and maybe even longer. And so what he wanted to do was be able to do that within seconds and maybe even under a second to really give more power to the creator. I think what's really interesting about that is that you have this ability by having it much more dynamic and feeling far more real time to really give more power to the creative people who might be working with this technology. I'll let Daniel explain more. Let's hop into the show. Hey, Daniel, thanks for joining me. I'd love to know more about kind of what was going on before you started this research and what were you up to?
Sure, yeah. So I was in grad school at Stanford. I recently finished my PhD there. And from the beginning of that process, I kind of knew that I was interested in using computation or artificial intelligence in particular to help with some kind of creative task. And I came from a computer graphics background originally. That's sort of what I focused on when I was in college. And so I was looking for applications or ways to contribute in that space. And pretty early on in my experience in grad school, I was exposed to a project that some other folks at Stanford did they called it Metropolis Procedural Modeling. And I want to show you a couple of examples if I can.
That'd be awesome.
Pull that up on the screen share. Yeah, so basically what's going on here is that what the authors of this system have done is they've written some programs. In this case, it's a kind of a simple class of program called a probabilistic context-free grammar, and they're using these to generate these random these tree structures. And that's kind of something that's been a staple of graphics for a long time. This idea of procedural modeling, writing programs that can pseudo-randomly generate 3D models or textures or images. But they had this really interesting idea to basically be able to also provide some kind of constraint on the output of these programs. And in this case, they're saying, well, if you view the tree from the top, then then this particular tree should look like the shape of the letter S.
Right.
And so what's going on here is they're using some automated techniques based on random search. And in particular, they're using a family of techniques called Markov chain Monte Carlo to do this. And when I saw this for the first time, I was really kind of blown away by it. I was really seized something in my imagination of, wow, you could write a program that could generate, any kind of structure you wanted, and then be able to provide some constraint, like say, make it look like this shape, and then say, hey, computer, figure out how to make that program do that thing. And it was kind of this really great synthesis of the programmer or the artist sort of providing their knowledge in the form of how to generate interesting looking structures, and then kind of letting the computer figure out how to do the hard work of controlling that and making that do something predictable. So that really appealed to me. And so I kind of started exploring this area and doing some work in that space. And that sort of became the focus of my dissertation work. And what I found out when we're working on this stuff, which everybody who works in this space does discover, is that these programs are really cool. They can do really interesting stuff, but you kind of find out that they're really slow. This process of of using random search to make the program satisfy these constraints takes a long time. And it's not always reliable. You run it, sometimes it works, sometimes it gets stuck and it doesn't actually make a nice looking result. So I'm gonna go ahead and end the screen share here.
Yeah. So you were working in the general space and you saw this work and it inspired you, or were you already working on something similar? Like what was kind of your path at that exact moment?
Yeah, I'd done a couple other projects related to kind of using AI or sort of semi-automated techniques for creating graphics content. But this was kind of one that really set me off on this particular direction. And so, I started getting interested in this idea of what can we do to make these things faster and more reliable, so that you can have, interesting procedural models, programs that you, the user, or some other person, some other artist wrote, and then make them be able to satisfy constraints quickly, so that you could say, interact with them. That it wasn't going to be something where you'd press a button and wait a few minutes and come back and you get a result, but hopefully you'd be able to do it in seconds or even less than a second for certain kinds of applications, so that you could then kind of have an interaction loop between the computer and the human user.
Yeah, that's interesting. And when you say, I think you mentioned this, but do you know how long those trees took, like per tree render?
Yeah, so those examples, they kind of like, this was kind of the first work in that space, and they really focused on just pushing this thing as photorealistically as they could get. So they were really high fidelity geometry, and I don't know off the top of my head exactly how long, but I know some of the results took hours to compute.
Oh, wow. Yeah.
So now that might be okay for somebody who's going to take one of those results and put them into, if they want to put it into like a computer generated film, they're already going to spend hours rendering things, so they're okay. But if you wanted these things to be usable in say inside of a game or some kind of interactive design tool, you kind of want that feedback loop to be snappier.
Right. Yeah. And you talk about even 2 or 3 seconds can be forever if you're kind of using a paintbrush type thing in Photoshop and you want it to be reactive. Like that could be a long time.
So I was interested in kind of pushing things closer to that interactive boundary. And it was around the time that I started thinking about this that the modern resurgence of neural networks was really taking off. And we were hearing, it seemed like every day you were hearing about deep learning this or deep learning that on the web or in the news. And suddenly all these machine learning systems started being able to do much more complicated stuff than they could before. Instead of just predicting a label for an image, they could generate you an entire image. And so seeing results like that was encouraging. And as I started learning more about some of the algorithms in the space, I started thinking, could we somehow have our programs, these procedural modeling programs, learn to satisfy constraints? Instead of them just kind of doing random stuff and then us enforcing constraints and trying to use random search to eventually get them to meet those constraints, what if we could somehow like embed some more intelligence in the program, so that as it was running, it kind of figured out what to do, and it wasn't just kind of randomly stabbing in the dark. And that was kind of, this particular project grew out of the desire to answer that question.
That's it. And was it something that just kind of hit you at a moment, or did you kind of slowly work through and say, hey, this is, I kind of like this piece and that piece, and you talked about getting that responsive feeling. Was there kind of an aha moment at all?
I think in a lot of, as is the case with a lot of research projects, I feel like there can be multiple aha moments. There's kind of the early one where like you get the seed of the idea and think, oh yes, this could be it. And then you try a few things and like inevitably none of them work for a while. And then eventually you kind of like, you scope the problem correctly to where like, this is the piece that I can make progress on. Mm-hmm. So I think the initial aha moment for me was learning about a particular family of algorithms that I could use. And it just kind of occurred to me like, oh yeah, this could be something that I could use in this case, in this particular setting. And so that was what sort of motivated me to go after this particular project.
Cool. So we're kind of alluding to your research. I'd love for you to kind of take us through a little bit of how you see your research.
Yeah, sure. So I think probably the easiest way for me to do that is to kind of explain it while going through a demo of what it does. So conveniently, I happen to have a little interactive demo you can play with on the web. Let me pull up the screen share for that. All right. So yeah, so as I mentioned, kind of the high-level statement for this project is I was trying to find a way to use neural networks to teach these kinds of procedural modeling programs, these graphics generating programs, to satisfy constraints. And so, what do I mean by a procedural graphics program? Well, I'm talking about something that generates an image by making some kind of random choices, like those those trees that I was showing before, those might generate those trees by kind of recursively generating branches where the length and angle of each branch is chosen randomly, and where to stop is also decided randomly. And as far as constraints, as in that project, in this one, I was focusing mainly on shape matching, or making the output of the program resemble some target shape, because that's kind of a nice way to impose some artistic direction or control on what's otherwise a pretty chaotic random process.
Right.
So, so I'm going to kind of demo this here. So, what I've got here is on the left here is this target shape that I'm going to want my program to hit. And then on the right, I'm going to be able to generate a bunch of different results. So I've got a couple of different programs I can use here. One which generates things that look like vines with flowers on them, and then the other one which kind of makes things that look like lightning bolts. So I'm going to click generate. It'll take a little bit longer the first time because it has to compile some code, and then I might get a result like that. I can hit it again, and it'll run faster the next time I do it. So, because this is a random program, every time I run it, I can get a different looking result.
Right.
And just to give you a sense for what the other program looks like, might give me something like this.
And so it's like, take us through a little bit about how that works. I mean, so it's kind of using that P and using some of the, maybe the boundaries to kind of better understand what type of constraint that you're looking for. Is that a good way to say that?
Yeah, so just roughly kind of the way it works is, as this program runs, so you can imagine as this thing runs, it might be kind of generating along like this particular lightning bolt here. And as it's running, it's making a series of choices. At some point it has to decide, like, I'm right here. Should I continue generating? Should I stop? If so, what direction should I keep going in? And you imagine, like, if you or I were trying to create one of these kinds of results by hand, and we were drawing, how would we do that? Well, we would be, we kind of have our pen or a pencil or our mouse cursor, whatever, on the canvas, and we kind of look over at the target shape and decide, like, okay, where do I need to go next? Do I need to go left or up or right? And so the program that I've written kind of does the same sort of thing. Like, it basically, as it's right before it's about to make one of these choices, it looks at both this target shape, and also it looks at what it's already generated so far, and it uses that information to figure out what choice to make and where to go next. And when I say that it looks at them, what I mean is that it feeds those inputs through a particular neural network that's been trained to make those choices well.
And so, I think there's a couple of really great examples inside this current P where there's like a branch of lightning, and then that particular branch ends. And is that a little bit also of kind of saying, like, hey, what have I drawn previously, and should I just stop this thing? Is that a little bit of that?
Yeah. So in theory, that this program is capable of learning. Like, at this point, it kind of knows, okay, I'm here, and I've already got this here, so I don't actually need to keep going. I can stop, and then let this particular execution of the program finish. And then maybe the next point it returns to is here, and then it kind of continues on from there. It's kind of doing this tree recursive process of growing into this shape.
Cool. And then is there a different, I see the drop down a little bit on the targets. Are there more different targets, and is there something inherently different about the targets other than the shape, or is there certain targets that are more interesting to you or less interesting?
There's just a bunch of different letter shapes we can use. Let's see. These are just I got the idea that having something that's kind of an immediate, like a stylized and interesting and immediately recognizable shape, like a glyph from a particular font, would be a really compelling example for this. So I just kind of looked around at different typefaces and found this one. I forget what this typeface is called, but there was something kind of, I don't know, nice and kind of script-like about its style, which I thought
it's a little bit different than the usual, at least the R that you had, right? It was a little bit of a unique R, which was kind of a cool shape.
Yeah, so in principle, you can use this for lots of different kinds of shape targets. Like, it's not limited just to font glyphs. But in fact, actually, I mentioned that I use neural networks to the program uses neural networks to kind of make these decisions about where to go next. And the way that those neural nets are trained is basically by looking at pairs of a target image and then a result like this, and it kind of learns how to mimic the choices that were made. And in fact, I trained this on shapes that are not like this at all. I trained it on a completely different data set of kind of random squiggles that were drawn in Photoshop. So despite the fact that it was trained on that, it was actually able to generalize to do interesting things like this, which is pretty cool.
That's really cool, and I feel like we keep running into examples of this when I'm going through all these different papers out there. It's amazing, and I had a guest on recently where we did procedurally generated chairs and different furniture objects, and they saw that and applied it to an entirely new domain, and I think it was faces in this context, and it worked pretty well. And so it's really interesting that there's starting to be this. I don't want to say movement because I don't think it's necessarily intentional, but these applications being cross-domain functional, which is super exciting.
Yeah. I mean, especially when you look at stuff like what OpenAI is doing with the universe and things like that. It's definitely something that's exciting for me too. I feel like like I mentioned, I come from a graphics background, and I feel like there's been a lot of work in graphics on generating interesting looking visual content, but it's often like somebody will publish an algorithm that works for one very specific use case. And it's gorgeous for that particular use case, but it's difficult to extract insights or let alone code that you could reuse to something else. So I like thinking about trying to build things that are a little bit more general purpose if possible. It's great.
Yeah, it just really opens it up, and I think it also opens up the accessibility for the general public. I just had dinner with an awesome couple last night, and we started talking about the podcast, and I was just explaining some random examples, and I think the ones that have that ability to jump across those domains for the kind of the layperson, it just makes it super accessible, which makes it really exciting. Let me take a moment to say that this wouldn't be possible without companies like Amazon.com. If you have experience with machine learning and are looking for a new challenge, they have over 100 opportunities available. Be sure to check out the link in the description, and let's get back to the show. So What was the most kind of challenging part of the research that you're working on? Was there something that really kind of gave you a lot of trouble?
Oh, there's lots of things. I think one of the things that was the most kind of an unexpected complication that popped up, which maybe shouldn't have been unexpected in retrospect, was that I had to really, in this particular project, I had to really be careful with the trade-off between how much complexity I put into the neural networks in the system, and then how much accuracy they gave me. Because in a typical machine learning setting, when you're trying to learn to predict, to classify something, or predict some labels or whatever, you're kind of willing to let the model that you build get as complicated and as computationally expensive as it needs to be, because generally it's going to still be a lot cheaper than the alternative, which is go get a person to label that thing, right? Which is like, in terms of computer cycles, that's like a massively expensive operation. In my case, I actually already had another algorithm that would work, which was these random search Monte Carlo methods. And so those will get better. The more time you throw at them, the more iterations you allow them to run for, they will eventually produce better results. And so I kind of ran up, in a couple of my early experiments, ran up against like, oh, I could build these really beefy neural networks, and they would do really well, but it turns out that they just get beaten by running random search with more iterations. And so I kind of had to find the sweet spot of like, what is the every extra bit of complexity I added to the system had to buy me something in terms of predictive accuracy. So if you go and you look at the paper and you look at the network that's described in there, it's fairly small compared to the giant convolutional networks that people are using for other stuff these days. But everything that's in there has a purpose, and it basically allows you to get extra predictive accuracy without slowing you down too much. So I feel like that was a new wrinkle that I wasn't expecting I was going to have to contend with. This was an interesting new angle on the problem.
Yeah, that's interesting. You kind of go through a lot of these, and that context, that trade-off. I mean, we make trade-offs constantly, and so it's always interesting to hear, specifically in these environments. And I think especially in the tech industry. I mean, I know, I work in a startup, and we think about scaling our servers and different things, and we have all these trade-offs of like, okay, do we work on this problem or that problem? Can we just throw more, buy a bigger instance, right? And we just solve it by throwing a little bit more money at it. And it's interesting to hear that on kind of the machine learning side as well.
Yeah, and especially in this setting when I'm working towards making things more interactive. It's like everything that slows you down is costly. So yeah.
Yeah, and so that's actually in this situation that time is a goal that you're working on and getting that response time, right? So the longer that process works, is actually working into your overall objective here.
Right, right.
Yeah, I see. I see. Um, by the way, what type of computer or what kind of setup did you run this research on?
Oh, sure, yeah. So I mean, this I did this all just on my laptop. You know, it's like a MacBook Pro from a few years ago.
Mhm.
And the environment that I used, so actually, this is probably a good example, a good opportunity to talk about the kind of framework that I used to do this in. I did not actually do this in kind of one of the big, big machine learning environments that's popular these days, like TensorFlow or Torch or anything like that. This was actually done in another language we've been developing. I've been developing with some other people here at Stanford, called WebPeople or WebPPL. It's kind of it's a language that's embedded in JavaScript, so it runs in the browser, which is why that I was able to show you that example I could show you before. And what it is it's an instance of something called the probabilistic programming language, which you or maybe other people in the audience might have heard the term floating around, and I know this is probably not the right venue to explain what those are in full detail, but suffice it to say that one of their purposes is kind of to make writing machine learning models look more like writing ordinary code, so that you can be both more productive, more accessible to people who aren't machine learning experts, and also make it possible to write some models that you just can't express in other kinds of frameworks. So yeah, so we built it in that, and so that's entirely in pure JavaScript. So the neural networks are not quite as fast yet as they are in say something like Torch or TensorFlow, which has a GPU backend and can be very, very fast. But like I mentioned, the neural net they ended up using was actually fairly small, so I think it actually was a pretty good trade-off.
Yeah, that's interesting. Yeah, I mean, the ability to be able to get this stuff to be more accessible, and part of my mission with the podcast in general is that I have a great team of engineers here at the startup I work at, and I think they're very interested in the ideas, but there's this seems to be this layer of abstraction in between it, and so I think anything that's increasing that accessibility, I think, only opens the potential contributors for the space, which is again super exciting. So, is there any additional stuff that you could show? I mean, I wouldn't want to restrain you from diving in. I do think there's a lot of decent amount of researchers that might be listening, so it might be worth taking the next step if you're open.
Showing.
Sorry, you mentioned not necessarily over explaining for the audience of what the PPL part of it was. I'd be interested in hearing if you think it might be relevant.
Yeah. Okay. I mean, I can sort of give you a brief kind of a brief primer on sort of how I see them, but the basic idea being that well, I mentioned before that I'm kind of using these to write these procedural graphics programs. They make random choices to generate images or 3D models, and then you kind of want to place some constraints on the output of that program, and then allow the system under the hood without you having to worry about it, just sort of reason backwards from those constraints to figure out what choices should the program have made to arrive at this particular output. And so you can actually use that. That has applications far beyond just these procedural graphics examples. A whole lot of machine learning can be phrased that way, where you have some data that you're interested in explaining some properties of. You might have some model, some process that you think gave rise to that data, some process that you think generated that data, and then you would like to ask the computer, hey, infer for me how this process ran in order to generate that data. So learn something about what hidden variables were involved in creating the data or something like that. So that's kind of the traditional pitch for probabilistic programming, is to say, well, let's just instead of having our users have to learn something about about all of the math, the intricacies behind how you write down and optimize these different kinds of machine learning models. What if we just let them express these models as programs that say, I'm going to write a random program that generates some data that kind of expresses my intuitions about how I think that data came to be. Maybe I think that there were some number of clusters the data was drawn from, or something like that. And then under the hood, the kind of runtime engine of this language is going to figure out how to make that model that I wrote jive with the data that I give it. So the intuition is hopefully, when these languages are still kind of in the early days, but when they're developed and they're usable and debugged and all that stuff, that all you have to know is really how to write some code, and maybe a little bit about different kinds of random sampling operations, like what a Gaussian distribution is, and that's about it. And then you wouldn't have to worry about all the details of these different optimization algorithms and things like that.
Yeah, that's cool. I mean, thank you for taking us through that. I find it interesting to learn all the little bit of the back end piece. There was a really great thread, I think, on Hacker News the other day about going through TensorFlow, and just hearing that whole conversation about the pros and cons and whatnot has been enlightening. So thanks for sharing.
Sure, happy to help out.
So what do you see as the most kind of potential applications for the research project that you worked on?
Yeah, well, I think that there's some obvious immediate applications. I think the kind of stuff that I showed in my demo, general kind of graphic design applications. You're trying to create decorative illustrations. Something like this, I think, it could fit very well in an environment like Photoshop. I think another application that's definitely not far off and that I've been interested in is, if you extend this from 2D to 3D, there's a lot of stuff you could do in creating content for games, other kinds of virtual world, virtual environment modeling applications. I think that's definitely on the table. And in a broader sense, I mentioned that we were just talking about probabilistic programming and how this was written in the probabilistic programming language. And I think the process of building research projects like this one, while this is kind of focused specifically on creativity and on a graphics application, this was kind of like a real stretch for the language, and it kind of helped stress test these languages. And in this case, it definitely led to the development of some new features, which are now kind of got merged from my crazy experimental branch into the main language and are now available in a more general setting for other people to use.
That's awesome.
Yeah, so that's cool.
Cool. So what are you kind of up to next?
Yeah, so that's a great question. I think there are definitely some continuations of this work that I think are exciting. I mentioned before when you were asking me about applications, I think doing this stuff in 3D would be awesome. I think that it could be pretty compelling way to interact with these kinds of procedural models. One thing you might imagine that you're in a kind of a VR setup, right? You've got like a VR headset on, and I don't know if you've seen any of the demos for things like Google's Tilt Brush. He's kind of painting.
Yeah, right. Yeah, and you can kind of like, I think with your hand, right, or maybe the Vive or the
you've got some kind of controller usually,
right? And you kind of squeeze. Yeah. Okay. Yep.
Yeah. So you can imagine like using that to sort of sketch out like a rough shape of, maybe I have a procedural description of, I don't know, spaceships for some 3D space exploration game. And I say like, well, I kind of want like my ship to look like this, and maybe I want some wings here and some engines here, and give me some gun turrets here. And then you just kind of say go, and the thing spits out something that looks like what you sketched, but is a lot more detailed and interesting.
Right. Kind of filling in where, man, that's really interesting. I mean, even I think of that with like a car design, right? It's like, okay, it's going to have 4 wheels, and so I want it to be in this general shape. Like you fill in the details, and it's interesting.
Yeah, exactly. So I think that VR is maybe a good direction for that, because it's it can be kind of difficult to interact with for casual users anyway. Difficult to interact with 3D with a mouse and keyboard. So so that could be cool.
Yeah, that's cool.
In this project, I was focusing mostly on these kind of I guess what I'll call like aesthetic constraints. Like I had this particular shape that I wanted to match. I was very interested in the appearance of the objects, and I think that it'd be really cool to start looking at some more functional properties of objects too. Like suppose I had a program that generated me different kinds of buildings, so like wild and crazy structures that I want to put in some new game that I'm making, and I want to make sure that my program, when I run it, only generates ones that are stable. So that my game's going to have, say, a physics engine, that they're going to be able to stand up under that engine, and then maybe later the player comes around and can knock them over or something.
Right.
So being able to make these programs that can kind of learn to satisfy that constraint, so they can just generate only the stable structures on the fly. I think that'd be very cool.
Yeah, that is the gaming application. It's actually kind of fascinating how many gaming applications a lot of this stuff kind of has, which I think is just a probably indicative of the space probably over time where we come up with these crazy ideas and then it's going to take some time to maybe have a commercial application outside of gaming. But yeah, I think of dynamically generated video game maps, and I'm a big fan of Battlefield 1 right now. And basically, like you'll walk up to this barn, and by the end of the match, the barn is basically completely obliterated and gone because all the bombs hit it and whatnot. And so thinking of generating those things, just make a barn in this general direction and generate an entirely new one that I've never seen before, even though I'm playing the same general theme or map or whatever. Seems like a lot of fun as a gamer, so that's cool to hear.
Yeah, for sure.
Cool. Yeah, go ahead.
I had a couple other things I was thinking about in this direction. I think that in all the research I've been showing so far, it's sort of assumed that these programs that we're trying to learn these constraints on, that we're given those programs. Somebody wrote them for us, but not everybody can write code to do something like that. So it's kind of been a long-standing problem in computer graphics, and how do you sort of learn these kinds of procedural models from examples, for instance? Because maybe somebody can't write code, but they can sort of sketch out a few different instances of what they want their thing to look like, and then you kind of learn them a program that generates more stuff like that. So lots of people have taken a stab at that over the years. But I think that now that we're in this kind of this modern era of AI and machine learning that we have now, with things like probabilistic programming, with the new deep learning technologies, I think it's probably time to revisit some of those ideas. And I have some thoughts along those lines that could be cool to explore.
That's awesome. And so are you thinking about, are you going to be still at Stanford now for a while and do some of that research, or are you going to branch off and start something, join something? What's kind of the actual day-to-day part of the next few months or years of your life?
Sure, yeah. So I finished my PhD at Stanford last year. I'm still here as a postdoc right now. And then actually next year I start a faculty job at Brown University. So that's kind of my next step, is starting my own research lab and hopefully getting to take some of this stuff and explore it further.
Yeah, that's awesome. That sounds a lot of fun. Well, cool. I really appreciate you joining the show. Any last parting wishes? Maybe 30 seconds. Anything you want to say?
Yeah, I don't know. I mean, I think I've done a whole lot of talking already, so I feel pretty good about where we're at. So yeah.
Cool. Well, I really appreciate you taking the time to show us through your work. It's really interesting. Is that URL that you were kind of playing around with, is that a public URL?
It is, yeah, absolutely. So
okay, cool. I'll go ahead and put a link in the description as well, so other people can play around with it. But thank you again, and thanks for joining the show.
Yeah, absolutely. Thanks for having me.